Hello, this is the last section of this course. So we have covered so far the ways we can model systems and analyze the behavior of systems. Now let's quickly touch on the last concept in this series, and that is the topic of control. So we'll be only touching on a little bit on what control is. We don't go into much detail. I just want to introduce the topic without getting into the fine details how you can design different kinds of controller. So just to begin, I have a few examples here of what we mean by control and what is the goal of control. So in the first example, you can imagine a car going on a highway. At some point it has a certain velocity. The car itself, if you put your foot off the gas pedal, given the initial condition, the car velocity tends to slowly decrease because of the rolling resistance in tires, aerodynamic drag, or many other sources of energy loss that exist in the car. What you want to do, you want your system, your car, to maintain its constant velocity. So that is the cruise controller. So that is one way of, one example of control, that we want our system to behave the way we want. Another example of a control could be a robotic system. So robots, you can apply torques to the motors, the robot moves, do something. So those robots are generally very heavy, they are non-linear and all of that. If you try to move the end effector of the robot, it may or may not respond the way you like it to respond. So ideally, especially human-robot interactions and the topic of collaborative robots or cobots, you often want your robot to behave kind of compliantly, as if there is a virtual spring that when you move your robot around, you don't feel the dynamics of the robot itself, but a completely different dynamics, as if you are just interacting, for instance, with a mass spring damper system. So you don't feel the true dynamics of the robot, and hopefully you don't get injured when the robot hits you. Maybe another non-engineering example that exists in biology. So in humans, in a resting state, the heart rate and respiration has a certain rhythm, and as you start to exercise, your muscles consume more energy and need more oxygen. So if your heart rate and respiration remains the same, over time the oxygen concentration in the blood will decrease because it is being consumed by the muscles. So what the nervous system does, it increases the heart rate and the speed of respiration such that you maintain a relatively constant oxygen concentration in the body. So this is also another form of control that happens within the body all the time and maintained by the nervous system. So from these few examples, you can kind of get the idea that the general goal of control is to make our system behave the way we want. And in very simple and fundamental way, the goal of control is to overwrite the dynamics of the system with a desired dynamics. So in all of these examples, instead of our dynamics of car velocity decreasing over time, we want to overwrite it such that we are now dealing with another system that essentially does not change over time. In this other example, we want to take the nonlinear dynamics of the robot through control, replace it by the dynamics of a virtual spring and damper. And in the last one, the body overrides the up and down dynamics of the respiration and oxygen concentration by a system that essentially has a constant response. So that is the general goal of control, that we want our system behave the way we want. So that's control as a general kind of concept. But general is a giant field, and the topics that are related to topic is not limited to engineering. Economy, biology, what else? What else do I have? I have a few examples. Engineering, economy, medicine, biology, sociology, all of these kind of have problems that are more or less related to controls. When we're talking about control, control is not a kind of one thing. There are many different classes of control. Classes of control. And you may have or may not have heard some of them. So we can have optimal control, which I'm a big fan of. Again, my pen is dying. Optimal control, there is robust control. There is a slightly older one, fuzzy, or I think it is spelled like that, fuzzy control, more modern AI and machine learning based controllers. So there are many different kind of categories or types of system. So this machine learning can also be different. Machine learning could be an optimal controller, or you want to design a robust controller using machine learning, and so on. So the list is, this is not an exhaustive list. In any of these classes, it is possible to have different architectures. Architectures. Kind of the two. Let me change. So the two important and kind of fundamental architectures, one is open loop control. And in open loop, as the name suggests, we have a system, we have our system. It receives some input. So we want to design the control input, that could be anything, control input U, such that the output of our system does something that we like. So this, as you can imagine, is not very robust, in the sense that if our real system, the physical system we are working with, is not exactly behaving the way we expect it to behave, what we give it as input may not necessarily give us the output that we like. And an important thing that can happen to these systems, maybe somebody bumps into your system and you keep getting the same, you're giving it the same input, but through this bump, now you start to diverge and go somewhere else. There is no way this open loop architecture to know what happened in the system and correct for it. So in some sense, open loop is a little limited, well, not a little, very limited in terms of what you can do with this control. On the other hand, we have another thing called closed loop control. And closed loop, as the name suggests, you have the system, and what you can do, you can measure something about the system. So I have this, I don't know, measuring device that measures the output of the system, and I take that and feed it to some control logic. This is my controller, that then my controller decides what inputs to give to the system such that my output behaves the same, the way I want. So two fundamental pieces in a closed loop control is, first, you need to have some kind of sensor to measure what is happening in your system, and then using that measurement inside a controller or a kind of a brain of the system to do calculations, decide what control input you need to apply to the system to get the desired response. So mostly the more kind of advanced and practical controllers are closed loop. There is a little bit of trade-off and a kind of an intermediate kind of control, and you can, I don't know, it has a specific name, but I'm gonna call it intermittent. I don't know if it has 2T or 1T, intermittent, and often open loop control. So examples of this. So this closed loop architecture is rather expensive to build because you need continuous measurement from the system and continuous decision that needs to be made, and probably your effectors that are changing the system are in this condition rather expensive because these control input can go up and down and do a lot of things, and you want to have actuators or effectors that affect the system to be able to produce that desired signal that you want. So that is a little bit expensive. What you can do, an example of this, is kind of wait for your system to reach a certain threshold and then activate something, and your system behaves until you reach another threshold and you change your course of action. So this concept of intermittent, that you apply, wait until something happens, you change your action, and then wait until something else happens. A very good example, a couple of examples, are in most of the thermostats at homes. So you define a set point temperature for the house. As in winter, the inside temperature drops, the system waits until it reaches a certain lower bound and then turns on the heater. So it goes from 0 to 100% heating capacity. So as you do that, then your temperature starts to increase, and you're monitoring it, and as it reaches a higher threshold, you say, okay, it's warm enough, and you turn off, and essentially this going up and down happens in the temperature of the house. Another example, a funny one, toilet flush. So as you flush, the water level drops, and at the same time the water starts to come in to fill it up again until it reaches a threshold, those buoyant things, and after a certain level of water, the valve is shut, so the water stays there until you flush again, and this happens. So these are a couple of examples of these intermittent open loop control, that you really are not modulating your control input, your signal U, it's a one on-off situation. It doesn't really have to be an on-off. Some controllers can produce interesting patterns. In fact, one of the important optimal control methods, called model predictive control, is roughly an intermittent control, but it is a lot more sophisticated and intelligent than just on-off. Anyway, so just to maybe summarize, open loop control is cheap but not very effective. Closed loop control, you can completely overwrite the dynamics of any system you want. So this is the most powerful one. Kind of a trade-off between are these intermittent open loop control. That can give you some level of control, but not the same quality as you would get in open loop control. I'm sorry, closed loop control. Okay, let me check if I have missed anything. Okay, good. So there is not enough room for me to do one example of control. So let me clean up the board, and I will come back to do one practical control problem. Now let's look at a control problem in the context of an example. So I have here an inverted pendulum. So the angle is measured from the upward vertical position. And because of that, if I linearize my equations of motion, I have such linearized system. And this T is an input torque that I'm applying at the base, at the pin joint. So you can imagine this is an electric motor that is attached to that joint. It can apply the torque however you want. So this could be your control input. But for now, and well, I have written the state space equations, or the equations in a state space form. Before going a bit further, let's analyze this system without the torque, so stability of the system on its own. So this is my A matrix. What I need to do is to find eigen values of A. To do that, I need, if it is A, solve A minus lambda I. Determinant of that equals 0. So what I would get is minus lambda 1 G over L minus lambda. Determinant of this is going to be lambda squared minus G over L equals 0. So from here I get two eigenvalues, that the lambda is plus minus the square root of G over L. We had seen this before, but because it is upward, I have a plus sign here, and this, given that G is positive and L is positive, which are my physical parameters, what I get is two poles that are both real. So G over L is a positive number. I take the square root, I end up with a positive number. So my two poles of the system without any control inputs or any closed loop control are here. And this one, lambda equals plus the square root of G over L. This one is positive. means that my system is unstable, which makes sense. So if I have my system upward here, I give it a tiny bit of disturbance or a tiny fling, the system will just fall. It will never go back to its original position. So let's try to design a controller that quote-unquote stabilizes the system. So maybe no, because I'm gonna leave my attempt 2 for later. So let's pretend, or not pretend, I want my system, instead of having just a pendulum that falls, I want my system to behave as if there is this spring attached to the base. So this is the desired behavior of the system, that you can imagine why I did this. So if my spring, if I move my pendulum to one side, hopefully my spring wants to push it back and keep it upright. So this is the desired dynamics I want to have. And to do that, I can design my controller to have my torque to be minus k times theta minus 0. And this 0 is the kind of where the resting length of the spring is. So this is my kind of reference position. So in simple terms, it's minus k theta. So I want to design my controller such that the motor torque is proportional to theta, and if theta is positive, I want my motor to push it back forward, and the size of the torque is proportional to the deviation from my reference point. And by doing that, I have essentially created a closed loop system. I need a sensor that measures the angle of the pendulum, and that goes to the controller. Controller decides that it requires this amount of torque, and if I apply to the system, I have essentially created this virtual spring using feedback control. So maybe I can draw the free body diagram, the block diagram of the system. This is my pendulum. I can measure angle out of the system, take this, multiply it by a minus k, and feed it as my control input or torque to the system, and now I have this closed loop feedback system. Now let's see how really mathematically that the dynamics of the new system look like. So starting maybe from here. So I have L theta double dot equals G theta plus, now my torque is minus K theta, which is, or it needs G over L, so I can factor out theta, so G over L minus K times theta. Now if I write this new system equation in a state space form, I have theta dot, my two states are 0, 1, G over L minus K, 0, times theta dot. Oh, this is d over dt of this. This is my new A matrix, A new. And if I want, now if I try to find the eigenvalues to analyze the stability of the system. Everything is the same except this G over L became G over L minus K, so blah blah blah. My lambdas will be plus minus a square root of G over L minus K. Now let's see what happens. So what I'm going to do is to draw these two poles of the system and analyze them where they go as I change my control gain K or the stiffness of the virtual spring. So originally I had my two poles here when K was 0. So if K is 0, I get the same eigenvalues of plus minus the square root of G over L. One of them is unstable, and that was the unstable system. And as you can see, if K is 0, you essentially have no input to the system, so it's the same system. As I increase my K, maybe let me try a different color. As I increase my K from 0, so this G over L is a number like, I don't know, 8.2, and K is 0.2, so 8.2 minus 0.2 is 8, so I have now plus minus the square root of 8, which is smaller. So essentially as I increase my control gain, I start to move this way toward the center. So K kind of increases. My two poles start to get closer and closer to each other until I reach at origin. My both poles collide. I have a repeated pole when K is G over L. So if K is G over L, my two poles are at the origin. Anything between that, so K, let me write it this way, K less than G over L, but bigger than 0, I still have one unstable pole and my system remains unstable. But funny enough, maybe change color. As my K increases beyond G over L, now this positive number G over L, a bigger number is subtracted from it. So I end up with a negative number under the square root, which means, so if my K is bigger than G over L, my lambda will be plus minus. It is going to be a negative number, so I can take out the negative number. It becomes a J square root of K minus G over L. Now, oh, this is equals. Lambda equals. And now what happens is as I increase my K, I'll have two poles. They are not really different color, that are imaginary. So my system no longer is strictly unstable. So as K becomes bigger than G over L, so my two poles start to go in opposite direction along the imaginary axis, and my system is out of instability. It is not completely stable yet. It is marginally stable. If you remember, if the poles are on the imaginary axis, we have marginal stability, and the system essentially oscillates back and forth forever without dying or diverging to infinity. which is expected from a system that has just a spring, so there's no energy dissipation, so it will continue oscillate forever. If you perturb it, it's going to move to a different amplitude of oscillation, but it will continue again oscillate with that new amplitude. So looking at where the poles go as I change my K value, I can try to see how the stability of my system changes. And this concept of showing the poles of the system or the eigenvalues as a function of your feedback gain is called root locus, or the locations of the roots. And this is a very powerful graphical description of how the system behaves under the influence of a controller. And you can visually see what are the good values of your K such that your system kind of behaves the way you want it to behave. So let me see. So kind of I mentioned it, but not explicitly. In order to stabilize the system and move it from unstable system to stability, you need to have a control gain that is at least bigger than G over L's, kind of the strength of instability of the actual system. So you want your feedback loop to be stronger than a certain amount to be able to stabilize the system. And kind of you can intuitively see if it's a very weak spring. If you perturb your system a little, the strength of the spring force that wants to bring the system back to its original location is not enough to overcome gravity, and the system will fall. And now you can see kind of very abstractly using the location of the eigenvalues of the system. Okay, so that's it. Let me double check if I have covered everything. So maybe one last item, that if you want to have a better response, for instance, instead of having these completely imaginary poles or eigenvalues, you want to have a system that shows kind of underdamped behavior, so it doesn't oscillate forever. It eventually comes to a stop at the top. You could kind of impose a virtual damper using the same torque. And what we do next in the next video, we try that. That would be our attempt number 2 in controlling the system. So think about this. Until next video, I'll see you then.